All right, so we are going to continue our study of continuous groups of transformations. And we're going to provide today a massively fascinating but unbelievably trivial example. So as a reminder, the continuous group part, that's all of this structure here. That's each of the elements of the set X is a group, and the group is expressed through these real functions phi, where phi is a function of the coordinates of each group element. And each group element has coordinates because X is a manifold. So this is a real function that provides the muth coordinate of the product of two group elements, alpha and beta, and that's sort of symbolized here in this green. The of transformation parts is that it's a reflection of the fact that each element of this group, it can be used as a tool to transform the basis of a vector space. And the function that takes an element of the group and an element of the and a set of basis vectors and produces another set of basis vectors, that function is f. That function is f. Now f takes its value in the field of the vector space. So it could be real complex or in principle quaternionic. And the book we're following, Gilmore, does in fact use this word continuous groups of transformations, and that's what we're concerned about. So we're going to run through this with an example, and it's Gilmore's example, and it's a really good one, and it's very straightforward and simple. So the first thing I'm going to do is I'm going to take this whole mapping, and we're going to keep it here to remind us of what's going on. And I'm now going to demonstrate the example. So ultimately, to create this example, I have to provide something to be transformed. Now in this picture, it's a vector space, and we're going to use a one-dimensional vector space for this purpose. But the transformation is going to be a little bit different. This isn't going to be an isometry transformation, right? We're not going to provide an inner product. We're going real simple here. So I'm going to create a set that will be transformed, and we will create a set of transformations. And our ultimate demand is we have to produce the function phi, which will take two transformations. Well, let's see, I guess I should write phi is this map from the Cartesian product of x and x back to x, and it will appear to take two transformations, which we'll use Greek letters for, and it will produce a third transformation. And then this has to, of course, be associative. It has to have inverses. And, of course, inverses means it must have an identity element, right? So it has to be a group, right? And then we also have to produce this function f. And f is a map from the vector space, the manifold, the group manifold, the continuous group manifold, the Cartesian product of that and a vector, which is another way of saying it just takes a group element and a vector, and it produces another vector, right? Now this also has to be associative, and it has to have inverse and an identity too. Right, so the transformation has to have these properties as well. That's an axiomatic piece of the story. I'm not sure if I think I demonstrated how it looks last time, but I didn't say it had to be that way. But yes, the postulates of a topological group has to exist, right? I mean, well, the function has to have closure, right? It has to have closure, it has to have associativity, identity, and inverse, right? The function f. Okay, so we are now going to create the example, and then we are going to check that it has all of these properties. So we will begin with a very simple number line, right? The number line starts at 0, and there is some point P on the number line. The point P is identified by name. Now it's pretty obvious that given this circumstance, we can create a coordinate for the point P, which we'll call x. And if we want to be technical, we'll say x is actually a function that takes a point and returns the number which is its coordinate. And to understand a coordinate system, it's usually good to introduce a scale, right? Normally you have you tick off marks, and then x is the sort of the position on the number line. That's all very dependent. The number x is dependent on the spacing between these marks, right? So another way of looking at that, which we'll use, is instead of ticking off marks, we're going to create a unit vector and call that unit vector E. Now, you can see this is a unit vector, which is a vector, so we're going to be in a vector space, so normally you would have multiple subscripts, right? But it's one-dimensional. We're only doing it once, so we're just going to use the letter E with no subscript at all. Okay, so the coordinate, so we're going to think of this coordinate x as in terms of this unit vector E, and therefore we're kind of thinking of P as a member of this one-dimensional vector space, and P is the numerical value x times the vector E. I better put a little vector symbol on it at least. And so x is the coordinate value and E is the unit vector. Right, so that's one of the things that is our setup. The other piece of the setup is this is still a number line, so we could imagine taking the location of the origin and shifting it, right? And if we shifted it, we would basically move it to just some new position, and that shift will be given by a certain amount, right? That's one of the things we can do, is we could in principle shift the position of the number line. The other thing we could do, I'm now talking about the things we could do to transform this arrangement, right? Because we've set up an arbitrary E, right? And x is dependent on that arbitrary E, but we've also got an arbitrary location for the coordinates. So we could imagine two things. We could imagine shifting the coordinate around, and we could also imagine rescaling E. We could take E and change it for some other vector, other unit vector. And if we did that, that would certainly change the value of x. So let's look at these two transformations. There are these two different transformations we're going to consider. The first is we take, let me go back to black. The first is we take the unit vector E and we transform that to a new number. And that number we're going to call 1 over alpha 1. Well, I'll put it as a superscript, E. So that is going to equal the new vector, we'll call it, say, E prime. So this is a transformation where we scale the unit vector into another vector. And this is one-dimensional, so it's just multiplication by a real number. We will insist that alpha 1 be greater than 0. So when alpha 1 is between, I guess, between 0 and hard stop 1, see, that should be soft stop, we're actually making E bigger, right? E becomes, bigger if alpha 1 is less than 1. And when alpha 1 is greater than 1, E is actually shrinking. Okay, so that's something we can do. And this is just a setup, right? I'm just showing you that we can do that. That's one choice. We'll call that scaling. Right? That's our scaling transformation. Then the other transformation is the possibility of shifting. Right? We're going to just shift everything over. So both scaling and, so the other one's shifting. So scaling and shifting. So both of these have an effect on the coordinates. Scaling is just a stand-in for changing our units on the number line, right? That's all we're doing here. It's modeled as a one-dimensional vector space, but the point is we're just basically scaling the units, right? So scaling and shifting. So how does that affect the coordinate of a point P? Well, if I scale the unit vector by 1 over alpha, then x will go to alpha 1 times x, and that's going to equal x prime, right? And if I shift the coordinates this way, then x is going to go to x plus the amount that I shifted, which we'll call alpha 2, right? And that's going to equal x prime. So this is for a shift, and this is for scaling. And if I'm going to do both, right, a general transformation will involve a scaling and a shift. So we'll agree to do the scaling first. So x under a combination of a scaling and a shift is going to be defined as scaling first on x and then the shift, right? So this is the execution of the transformation. All right, so we have two different numbers we need to describe this transformation, two different numbers. And one is a scaling and one is a shift. Therefore, we will have to have a notation to describe a full transformation. So we could do a couple things. We could say, oh, a full transformation takes two numbers. We'll call it alpha 1, comma, alpha 2. It'll be this ordered pair of numbers. We could also, since we're going to do it a lot, let's just agree that if I put alpha 1 and alpha 2 next to each other, I'm really talking about a transformation that scales by alpha 1 and then shifts by alpha 2, right? So if they're next to each other, and we can move between these two things, right? But a full transformation has two numbers in its identity. Two numbers describe the whole darn thing. So if I just want to shift, then it would have to be something. If I wanted to just scale, it'd be alpha 1, 0, like that. That's not 0 times alpha 1. That's a shift of alpha 1, or a scale of alpha 1 and a shift of 0. I'm going to be screwing up saying scaling and shifting between each other a lot, I'm sure. Likewise, if I was going to not shift at all, or not scale at all, but shift, I would go 1 and alpha 2, right? That would be a no scaling and a shift of alpha 2. But this does bring up an important point. What's the unit? What is the identity? The identity element would be 1, 0, or I guess we would write it maybe something like that, 10, in our shorthand notation. The shorthand notation will almost always be used when there's two non-defined or arbitrary scales and shifts. But anyway, this is the unit. So that is good because that's one of the check marks, right? We have to show that this function that there's an identity involved, right? Now, we haven't shown that there's inverses, but this is the transformation that we are going to consider. So that's this transformation. So there's going to be some function that's going to take a member of the group and execute this transformation. So now we can start thinking about how to fill in these ideas up here. So in this case, this set here, the set that's going to be subject to the transformations, right? It's not going to be a vector space with n dimensions and an inner product on a field. That's kind of what we use to articulate what a classical group was. We can still have a continuous group that executes a transformation, but not on something so complicated, right? We're just taking our set to be the coordinate x. The coordinate x, which is essentially a one-dimensional real vector space, right? So you could think of it that way. We don't know inner product at all, right? Because we're just thinking of the super simple one-dimensional vector space. But this notion of shifting the coordinate, that doesn't really exist in a vector space context so much. The scaling certainly does, right? That's obvious. But there's also this shift thing. But ultimately, it's a one-dimensional vector space that we're playing with. And so now we're going to replace this with, well, that's what x will be, our coordinate x. And then what is the group operation? Well, the group operation will be the full transformation alpha, which is going to actually be alpha 1, the scaling, and alpha 2, the shift. And we might write that as alpha 1, alpha 2, as I just said. So Greek letters are objects that live in here, and Latin letters, well, x, the coordinate x, will live up there. And so now the question is this, can we understand this to be a manifold, right? It certainly has two parameters, and gosh, this looks like coordinates the way I've suggested we write it down. But my suggestion was just to keep track of the scalings and the shifts. but I end up putting it in an ordered pair, so there's really nothing stopping me from taking the next step and saying, well, I can make, I can make an axis, alpha 1, alpha 2, right? And that is R2, right? So every shift and scaling that's up there, I can plot in R2, or can I? Let's see. I can't use the real law, I can't use alpha 1 equals 0, right? If alpha 1 scaled this to 0, then that's no good. That's not a legitimate transformation. So the blue line is out. I could, in principle, use negative numbers for alpha 1, though, because flipping the sign of E1 is okay. But let's restrict, but I've already said alpha 1 is just going to be greater than 0. So I'm really forcing myself to just use the right half plane. The shift, of course, can be any positive number. I can shift by 0, I can shift by 1,000 or a negative 1,000, right? So shifting can go everywhere. So I have now established a map from every point in the manifold to the right half plane, every legitimate point, meaning alpha 1 greater than 0, to the right half plane, not including this line here. And all that's going to be really important. This example is quite rich. So the fact that this line's not part of it is going to become important. And then we're going to talk about this side eventually too. We're going to add the transformation to flip. We're going to relax this restriction later on. So, but the point is that this is clearly a mapping from all possible transformations to R2, which it's a pretty literal mapping. I just take these two numbers and I plot them, right? So these can now be considered coordinates. These can now be considered coordinates, and I've established essentially that this is a manifold. So I suppose we could go through all the work of showing, well, okay, so now that we know that, now we established that it's a manifold. The transformations are a manifold, but that's not the same as saying the transformations form a group, right? I have to show that these transformations form a group. So how do we do that? Well, we go back to this original point. We need to show that this map exists, meaning I have to create the map phi, which takes two group elements, produces a third, shows that it's associative, shows that it has an inverse, and shows that it has an identity. So I'm going to kind of do that quickly because you can sort of do it yourself. So the first thing we have to do is we have to define phi for two group elements. We have to be able to take the coordinates of these group elements, beta 1, beta 2, alpha 1, alpha 2, right? I guess maybe this is a good place to put commas, I suppose. And we have to end up with the coordinates of gamma. We have to end up with a gamma 1, gamma 2, right? We have to figure out what is this expression, right? Another way to write this is gamma 1 or phi 1, and then I just put gamma 1 there, and then I write the whole thing again for phi 2, beta 1, beta 2, alpha 1, alpha 2, and I get gamma 2. That's another way of doing it. Probably the most logical way is phi mu gamma mu, like that. Okay. So we have to figure out what that formula is. Not too tough, right? Because these things are defined by how they act on the coordinate, right? So what I do is I say if x prime, if x prime equals, say, alpha 1 x plus alpha 2, right? That's using the transformation alpha. And then I say x double prime equals beta 1 x plus, or x prime plus beta 2. That's for the transformation beta on x prime. Then I'm just looking for a transformation of x that takes us directly from x to x double prime. Right, so what would that look like? Well, x double prime is just simply beta 1 times alpha 1 x plus alpha 2 plus beta 2, which obviously equals beta 1, this is alpha 1 x. Beta 1 alpha 1 x plus beta 1 alpha 2 plus beta 2. And so doing alpha and then beta results in gamma, where gamma 1 is beta 1 alpha 1 and gamma 2 is beta 1 alpha 2 plus beta 2. So that's the formula. So the formula for taking two operators or two transformations together, what's the third transformation? That's what phi is supposed to be. Phi is supposed to be gamma. So the answer is, well, this is the answer, right? So you should say phi 1 of beta alpha is going to equal beta 1 alpha 1. And phi 2 of beta alpha is going to equal beta 1 alpha 2 plus beta 2, right? And that is our defined function phi. So we have now created phi, right? We've got it. Phi is what I just figured out over there. So now what about f? Well, f we already knew. F we kind of figured out right in the middle of everything, right when we did this calculation. Where was it? Right here, right? This is f. F of alpha and x equals alpha 1x plus alpha 2. That's f, right? Now again, now notice, first of all, I don't need to say fi because this is all one-dimensional, or f1, right? Because we only have x. But if we had multiple dimensions in our underlying space here, if this guy was higher dimensional in our example, we would need an f1 and f2. So we now know f and we now know phi. So all we have to do is we have to prove that f and phi satisfy these rules, right? Satisfy which rules? Where did I put those rules? Right here. They are associative, inverses exist, and they have an identity. So let's knock that out. The hard one is associativity, but this, once you have phi, this is what associativity means. Phi operating on a transformation gamma. So now we have three separate transformations, beta, alpha, and gamma. Gamma is no longer defined through, don't worry, gamma is no longer defined through this process here, right? This is not, this was an example for gamma, where gamma was a product of alpha and beta. Now gamma is just an independent thing. So this is the definition of associativity. The group product between gamma and the product of alpha and beta, or beta and alpha, is equal to the product of gamma and alpha with beta. So we have to show that this side and this side are equal to be sure that we have associativity. So we can just blow up the arguments, right? So gamma is really gamma 1, gamma 2. Remember, this has to be a real number. Everything in here is real, and the result is real. So gamma, this is shorthand for gamma 1, gamma 2. And this guy, we know what that is. We know the formula, so we just execute the formula. And we know that its first component is beta 1 alpha 1, and its second component is beta 1 alpha 2 plus beta 2. So now we just run the formula on these things, and what do we get? And we get this. The phi 1 form, right, is phi 1 beta 1 alpha 1, and then the phi 2 coordinate is going to be phi 1 times beta 1 alpha 2, phi 1 plus times beta 2 plus gamma 2. All right, so now we check this side. Okay, so here's the breakdown of these coordinates here, breaking down phi into the phi 1 part, the phi 2 part, breaking down beta to the beta 1 part, the beta 2 part, and now we'll look for phi 1, right, which is going to be the product of the two scale changes, which is gamma 1 alpha 1 beta 1. Then we'll look at the phi 2 part, which is going to be the scale change times the second shift change, which will be, wait a minute, I did something wrong here. Yeah, see, look, I went phi alpha beta, so it's, yeah, I can't change the order of things, right? This is gamma beta alpha. This has to be gamma beta alpha. So that has to be a beta and that has to be an alpha. So I got to fix this. Let's see, I got to do that and that. So that has to be a beta, that has to be an alpha, and then this has to change. Okay, so that changes to this, and then this has to be gamma 1 beta 1 times alpha 1. So that's fine. But now this has to be gamma 1 beta 1 times alpha 2, right, for this one. Gamma 1 beta 1 alpha 2 plus the shift of the first part, which is gamma 1 beta 2 gamma 2. Okay, so notice that everything's right. This and this are, oops, there's a plus sign missing, are equal. And likewise, this and this are equal. So the associative property holds. So that was the demonstration of the associative property for phi. We should check the associative property for f. So that analysis looks like this. F of phi beta alpha acting on f, which is saying what is the transformation of x given by the transformation that is the product of beta and alpha. So we take the product of beta and alpha, find that transformation, act on x. Or I can take alpha and act on x, and then beta and act on x, on the result. Then I can take the result of each transformation successively. That's what associativity means in this context. What it's a little confusing is x is not a transformation. It's what's being transformed. Yet you can still speak of associativity because we would normally, you would just write it beta after alpha x. So the question is, do I have to do beta after alpha and then evaluate on x? Or do I do x on alpha and then beta after x on alpha, right? Shouldn't matter, right? Shouldn't matter. So if I do it this way first, this product is easy to evaluate. It's just beta 1 alpha 1, beta 1 alpha 2 plus beta 2 x. And then this guy is easy to evaluate because we know the formula. It's going to be the scale and the slope applied to x. So scale x first, which is the rule, and then add the slope, and you get this number. So the question is, does this end up being the same thing as this? Notice what's interesting here is you end up with a group operation in this side first, and here's just two successive transformation operations. So f shows up twice on this side, so it's a little asymmetrical compared to this examination. Okay, so let's see what this is. So the first step is I'll blow this up into beta 1, beta 2, just to describe both of its coordinates, and then I'll evaluate this to be alpha 1 x plus alpha 2. So this is the new transformed vector. This is x, or transformed coordinate. This is x transformed by alpha 1, alpha 2x. So, so now I just execute this, right? And clearly you can see that this is just going to be the scaling times the scaling on x, and then it's the scaling times the first shift, which is this, and then it's the second shift, which is that, right? And this, in fact, equals that. So these are associative. So to show inverses is pretty straightforward. You have to show that for every alpha, you can find an alpha inverse, and your expectation is that the result is going to be 1, 0, right? That's the, now we have to kind of lean into this ordered pair notation, but it's going to be a scaling of unity and a shift of 0. And this isn't too difficult to see what a likely inverse is. So we would just say phi, let's do it the other way. Let's do it the other way just to make it a little bit easier. Alpha, alpha inverse. Fortunately, inversions are always going to be commutative. And so we have alpha 1, alpha 2, and 1 over alpha 1 will certainly make it so, let's see, undo. The reciprocal of alpha 1 will certainly take care of phi 1. Phi 1 will end up equaling alpha 1 times 1 over alpha 1, which will equal 1, so that's good. And then what do we need for 0? Well, we're going to need minus alpha 2 over alpha 1, right? So now phi 2, which will end up being alpha 1 times minus alpha 2 over alpha 1 plus alpha 2, and that, of course, is going to equal 0. So now we have to look at this and say, okay, does this always exist? Well, alpha 1, we've already asserted alpha 1 is greater than 0. So we know that that exists, and therefore that exists too, and there's no restrictions on a negative number for the second term. In other words, the shift term can be negative. We're keeping the scale term to be positive. So this inverse always exists. So yeah, so we have an inverse for the group operation function. Now we check the inverse for the f function. We will look at, so let's take that inverse, right, and see if it acts like it should, right? If we have 1 over alpha 1 minus alpha 2 over alpha 1, right? That's the operator, and then it's going to act on x, which has been transformed by alpha. So it's acting on alpha x, right? Well, what's alpha x? Alpha x is alpha 1 x plus alpha 2. So we're looking for f of 1 over alpha 1 comma minus alpha 2 over alpha 1 acting on this particular coordinate, alpha 1 x plus alpha 2. It should undo the alpha. This operation should undo that one. And so, well, what is that result? That result will be 1 over alpha 1 times alpha 1 x plus alpha 2 minus alpha 2 over alpha 1, which of course is x plus alpha 2 over alpha 1 minus alpha 2 over alpha 1, which equals x. So it does in fact undo it. So the inverses exist. So good enough. We've sort of shown everything that we really need to show about this. All right, so let's review our example, because we're going to go through, we're going to use this example quite a bit. We've replaced this space that is subject to the transformations with really this sort of one-dimensional vector space. And we've defined the transformation itself to be the shift of the coordinate, right? The shift of the coordinate. So given a transformation where I can scale and shift, the function that does that, this f, will take the coordinates of the transformation itself, right? The transformation itself is given by a coordinate alpha 1 and alpha 2, and it takes those two real numbers, and then it takes the real number for x, the vector, or the coordinate of the point P, and it transforms it in this very, very simple and straightforward way. And we've shown it's associative, and we've shown that it's subject to the inversion as well. And knowing that, we were able to define this function, the two successive transformations, alpha, beta, and alpha. So this would be beta after alpha, right? If you would write it in sort of group form, it's beta after alpha. And this guy breaks down into, remember, this is going to produce another transformation. So how many? You need 2 dimensions, right? We have a 2-dimensional manifold of transformations. So we are taking beta 1 alpha 1 as the first dimension, and then beta 1 alpha 2 plus beta 2 as the second dimension. So the reason we have 2 here is ultimately because of the dimensionality of our manifold of transformations. And the reason we have only 1 here is because of the dimensionality of our vector space. In this case is 1. So this fits everything. We checked associativity, we checked for inverses, we've got closure, So these guys are a group. This is behaving correctly. There's not much else to say about it. Oh, there was a chance to point out contravariance and covariance, which I missed earlier. We've said that E is going to go to 1 over alpha 1 E. So E, I guess, E vector prime. So we're scaling the unit vector by 1 over alpha, which results in scaling the coordinate by alpha 1. That's why you have alpha 1 here as a product, even though when we define the scaling, we defined it in terms of 1 over alpha 1, right? Shrinking this unit vector increases the value of the coordinate. That's because the relationship between the coordinate and the unit vector is a contravariant relationship. Under the transformation of scaling, they have a contravariant relationship. They transform in opposite ways. This transforms by dividing by alpha 1. This transforms by multiplying by alpha 1. So the unit vector kind of falls into the background in our story because we're dealing with everything in terms of the coordinate in this case. When we did the what is a tensor series, we kind of focused on how the unit vectors transformed. But here it was a little easier to do it in terms of the coordinate. So this is our great example. Know it well. Make sure you are comfortable with what these functions mean. This is the function that has to do with the of transformations part of the definition of a continuous group of transformations. And this is the continuous group part. This is actually it captures both the continuous and the group, because this is a real valued function. And so the function and so these have to be continuous functions from here into here. The topology of the group, the topology is what establishes that. But this is also the group function because it takes two group elements and it produces another group element. That's the group operation. So it's the group operation expressed as a real function that is continuous. And that's why it's a continuous group of transformations. Okay, so we're going to next take this example, and we're going to start pushing into a lot more abstract stuff. I may have to do a very quick down and dirty review of some particular element of group theory that becomes important, but that'll be for the next time. Thanks.